So in question 6, we're given a particle of unknown mass. We're told it's placed in a rough plane at angle theta to the horizontal. We're given the sine of this angle. We're told that it's kept in equilibrium with this force P. And we're told the coefficient of friction between the plane and the ball. We need to find the least possible value of P. So just the value of P that will keep this ball at rest. So we need to consider the forces that are acting here. So firstly, we will have the gravitational force, mg. We will also have the normal force, which we will call r. And we need to think about which direction the frictional force will act. So this force would be wanting to push the ball upwards. The ball would be wanting to slide downwards originally, and therefore the frictional force is going to be pointing up the slope like this. So we can just say that this is mu times the normal force. Again, because the ball would want to slide down on its own, therefore the frictional force is acting opposite to this as to oppose this change in motion. And well, the strategy we need to write up here is the sum of the forces. We know that the sum of the x component of the force is 0, and we know the sum of the y component is also 0 because we're in equilibrium. And what we like to do is usually make a coordinate system that is parallel and perpendicular to the plane. So we will have to split up each of these vectors into these components. So this is here theta. So this will just be mg cosine theta. And then this horizontal component will be mg sine theta. And we do the same thing with this unknown vector p. So we know that the angle here is theta. And so we can again look at this vertical and parallel components with the slope. So this will be p sine theta. And this bottom one will be p cosine theta. And we know that this has to act downwards, this has to act to the right. That's how they will create this net force of P. So now we can write up the sum of the forces in each of the directions. So we can say that mg cosine theta, so the vertical forces, so mg cosine theta will be equal to r plus, so we have r acting upwards, mg cosine theta is acting downwards, so this will be equal to well, perhaps I'll write it like this. So this plus p sine theta, so the forces that are acting downwards is equal to the force that is acting upwards, which is just r. And then we can do the same thing for the horizontal forces. So we can say mg sine theta is acting to the left. So we have mg sine theta, and this is equal to, so this is acting to the left, everything else is acting to the right, and therefore this will just be p cosine theta plus mu times r, right? Both of these forces are simply acting to the right. All right, and now we need to solve for p. So we know what the sine of theta is. We also have a cosine theta here, so we could quickly find what the cosine of the angle is. If we just draw a little triangle here, we have theta. We know the sine is opposite over hypotenuse. This is opposite, this is hypotenuse. And then we can also find the adjacent side. This will be 24, simply using Pythagoras. So the cosine of the angle is adjacent over hypotenuse, just like this. And then we just need to, for example, here, this equation in terms of r, we can just plug this equation for r in here as it's an unknown. So we can say mg sine theta is equal to p cosine theta plus mu times the r, so mg cosine theta plus p sine theta. And well, now we can just plug everything in. So we know that the mass is 1.2, g is 10, sine of the angle is 7 over 25, and this is equal to P, that's our unknown, times 24 over 25 plus 0.15 times 1.2 times 10 times 24 over 25 plus P times 7 over 25. And then here we just have to, we can factor out a P and just divide. Either way, we will just find that P is equal to 1.63 newtons.